Okay, guys, welcome. In this video, we're going to talk about doubling time and half-life. Okay, so now doubling time, of course, is the time required for each doubling within an exponential growth model. Now, after a time t, an exponentially growing quantity with a doubling time of capital T double, which a lot of times I'll just write as capital T, increases in size by a factor of 2 to the t over capital T double. Now, the new value of the growing quantity is related to its initial value, which of course is when t equals 0. And you get that the new value is equal to the initial value times 2 to the t over capital T or T double. Okay, so let's look at an example regarding that. Now, compound interest produces exponential growth because in an interest-bearing account, you'll grow by the same percentage each year. Now, let's suppose that your bank account has a doubling time of 13 years. By what factor does your balance increase in 50 years? Well, again, remember that we have that y is equal to your initial value times 2 to the little t over t double. Okay, well here, our initial value we can say is just 1 because we're only interested in what factor does your balance increase in. Now 2 is always 2, and now our little t is how much time we want to enter in, and that's 50 in this case. Now capital T double that's given to us, that's 13 years, so I'm going to put a 13 down here. So now I need to do 1 times 2 to the 50 over 13, okay? So for this, we're going to need a calculator. So if we enter this in, we're going to have 2 to the parenthesis 50 over 13. And that's going to give us that y is about 14.38. Right? So in 50 years, you're growing by a factor of 14.38. Okay, in the next example, we have that world population doubled from 3 billion in 1960 to 6 billion in 2000. So we'll suppose that world population continued to grow after 2000 with a doubling time of 40 years. So what would the population be in 2050 and then in 2200? Okay, so again, we're using the formula y equals, and I'll call the initial value y0 just to make it a little easier. And then we'll multiply it by 2 to the t over capital T. So for 2050, we're going to have something like y is equal to, and of course it depends on which one you want to use as your initial. I'll use 6 billion in 2000 to be my initial time. So we'll say that this is y is equal to 6 times 2. And if I want to get to 2050 and I'm starting at 2000, then that's 50 years. And my doubling time is 40 years, right? So I need to do 6 times 2 to the 50 over 40. Now, you could have also done this by using 3 billion, but of course that would be in 1960, so then you would have to make your little t equal to 90 there, right? Because it's 90 years from 1960 to 2050. But either way, you should end up with the same thing, and if we do this, we're going to get 6 times 2 to the 50 over 40, and we're going to get that y is equal to, y is equal to 14.27. And of course, this is in billions. Okay, now if we do the same thing for 2200, right, we'll have y is equal to, and I'll start at 2000 again, just so it'll make our t value nice. And we're going to get 6 times 2 to the now, how many years is it from 2000 to 2200? Well, it's 200 over 40. So we're going to get that y is equal to, once we enter this in, right? So this is just going to become 6 times 2 to the 5th once we simplify, and we get 192. Right? And of course, this number would not be possible, right? Because you're going to run out of room on the planet, right? So that's something that we would have to keep in mind. Now, there's an approximate doubling time formula, which is sometimes called the rule of 70. Now, for a quantity growing exponentially at a rate of p% per time period, you can approximate the doubling time by taking 70 and dividing it by p. Now, this approximation works best for small growth rates, and it will break down once you get for past growth rates of around 15%, right? So this approximation is best if your percentage is small, right? So now in this example, we have the world population reached 7 billion in 2012 and was growing at a rate of about 1% per year. So we want to know what is the approximate doubling time at this growth rate. And if the growth rate were to continue, what would the world population be in 2050? And we'll compare this to what we got in example 2. All right. So now to get the approximate doubling time, I need to take 70 and divide it by p%. Right. So in this case, it's 70, and I shouldn't say p%, it's just 70 divided by p, where p is the percentage. So in this case, I need to take 70 and divide it by 1.1. So if we do that, 70 divided by 1.1 is going to give us the doubling time is about 63.63. Okay. Now we're going to assume that the growth rate were to continue and compare this to the world population in 2050. Now, here we're given that we're starting at 7 billion in 2012. So we're going to have something like, again, y equals a times 1 plus p to the x. So we're going to get that this is 7 billion times 1. Oh, wait, I should be using the doubling formula. Sorry about that. So we should have y0 times 2 to the t over big T. So we're going to get 7 times 2 to the little t, which if I'm going to 2050 from 2012, that would be 38 years. And my doubling time is 63.63. So we're going to get 7 times 2 to the parenthesis 38 over 63.63. And we get that our y is equal to 10.58 approximately, right? Which is a little bit less than what we calculated in this other example, right? In the other one, we found it to be about 14.27 billion. Okay. Now, in example 4, we have the world population doubled in the 40 years from 1960 to 2000. What was the average percentage growth rate during this period? Right. Now, contrast this growth rate with the 2012 growth rate of 1.1% per year. Okay. So now we doubled from 1960 to 2000. Okay, now to get the average percentage growth rate, we can use our doubling time formula, right? Because we know that we have something like 2 is equal to 1 times 2 to the, I guess we don't want to use that, right? So here we want to do something more. Now, one way we can do that is that we can calculate using the fact that t double is approximately equal to 70 divided by our percentage p. Now here we want to find p, and we're going to have that our doubling time is 40, and that's equal to 70 over p. Now, if you think of 40 over 1, 40 is 40 over 1, and you cross multiply, you'll find that 40p is equal to 70. So p is roughly equal to 70 over 40, which would give you that p is 1.75, right? So you have that your growth rate is 1.75%, right? So it's close, but not quite the 1.1% that we found. That we were given, I should say. Okay, now just as we have doubling time with exponential growth, we can also have exponential decay which will lead to half-life. Now, exponential decay occurs when a quantity decreases by the same percentage each year, or every fixed time period. And in that case, the value of the quantity repeatedly will decrease to half of its value. And of course, each halving will occur in a time that we refer to as the half-life. Now, this is essentially the same formula that we had as we did for doubling time, only here instead of 2 to a power, you now have 1/2 to a power, and then it's little t over t half, where t half is the half-life. Right, so it's essentially the same type of calculation. Okay, now in example 5, we have that radioactive carbon-14 has a half-life of about 5,700 years. So it collects in organisms only while they are alive, and once they're dead, it only decays. So what fraction of the carbon-14 in an animal bone still remains 1,000 years after the animal has died? Okay, so if we say that the initial value is 1, then we can find what fraction remains. So we're going to have y is equal to 1 times 1/2. Now we have that 1,000 years passed, and the half-life is 5,700. Right, so now we just enter this into the calculator. So we got to find 1/2 on parentheses to the 1,000 divided by 57. And again, that exponent should be in parentheses. And we'll get that y is equal to 0.8855 about. Right, so after 1,000 years, you have 88.55% of what was originally in the animal bone. Okay. Now, in example 6, suppose that 100 pounds of plutonium-239 is deposited at a nuclear waste site. How much of it will be present in 100,000 years? Now, I forgot to put the half-life of plutonium in here. So if let me pause it and I'll look that up real quick. Okay, so the half-life of plutonium is 24,000 years. So now if we deposit 100 pounds, then we're going to plug it into our formula. And then we're going to get 100 pounds times 1/2. Now we want to know how much is present in 100,000 years. So I'm going to have to the 100,000 over 24,000. So of course, if we enter this into the calculator, I need to do 100 times parenthesis 1/2 to the parenthesis 100,000 divided by 24,000. And that will give me that we'll have 5.57 roughly. So we get that after 100,000 years, this 100 pounds will have decayed to 5.57 pounds. Okay. Now, just as in the example for doubling time, we can also approximately relate the half-life to the percentage by this rule of 70 again, right? So if I take the half-life and I have that approximately equal to 70 over P, where P is the percent per time period, then for small decay rates, this will closely approximate what the percentage rate is. Okay, so in example 7, we're going to suppose that the inflation causes the value of the Russian ruble to fall at a rate of 12% per year. At this rate, how long does it take for the ruble to lose half of its value? Okay, so we're going to have that T half, of course, is approximately equal to 70 divided by 12. So of course, this will give us, if I do 70 divided by 12, I'm going to get that the decay rate is about 5.833%. Okay, or not percent. This is for T half, so this is just years. So it will take 5.833 years for it to lose half of its value. Sorry about that. Now, in the previous examples, we just looked at the rule of 70, for the exact, for approximate formulas for the doubling time and half-life. Now, you can actually find what the exact percentages are by using these formulas with logarithms, right? So if you're familiar with logarithms, you can use the logarithm key on your calculator to figure out what the exact doubling or half-life time is. Okay, so let's see that in this example, we have a population of rats that's growing at a rate of 80% per month. We want to find the exact doubling time for this growth rate and compare it to the doubling time found with the approximate time formula. Okay, so the exact would be that the t double is equal to, now if we look here, it's log 2 over log of 1 plus r. So in this case, I want to do log of 2 over log of 1 plus 0.8. So if I do that, I'm doing log of 2 divided by log of 1.8. And that will give me that the doubling time is 1.18. All right. And then, of course, for the approximate, we get that t double is approximately 70 divided by p, which is 80. And if we do that, we get that this is 0.875. Right. And of course, the reason why this is off by so much is because remember that the approximate one works best when p is small. And of course, here 80 is not small, right? It's much bigger than 15%. Okay, now I believe this is the last example. Yep. So suppose the Russian ruble is falling in value against the dollar at 12% per year, and then using the exact half-life formula will determine how long it takes for the ruble to lose half of its value. So the exact, remember, is t half is equal to minus log 2 over log of 1 plus r. Right, let me just make sure that that is correct. Yep. So of course here, we have minus log 2 over log of 1 plus r. So now in this case, we have minus log 2 over log of 1. Now since r is negative, it's minus 0.12. Okay, so now if we calculate this, I have a minus log 2 log 2, and then divided by a log of 1 minus 0.12, and we'll get that the half-life is 5.422 years. Now, if we compare that with the value that we found, we get 5.833, which is pretty close. And of course, the reason why it's much closer here is because that percentage is less than 15%. So that should give us a better approximation. Okay, well, that concludes this video on doubling time and half-life. I hope you enjoyed, and I'll see you next time.